In episode 21, titled OSPF versus BGP, Which Problem Each One is Solving, we frame protocol choice as an interdomain versus intradomain routing decision, because that single distinction explains most scenario answers without getting lost in vendor trivia. When you choose open shortest path first, you are usually solving how to route efficiently inside one controlled environment that you own and can standardize. When you choose border gateway protocol, you are usually solving how to exchange reachability between networks that have separate ownership, separate policies, and separate reasons for preferring one path over another. The exam often tests this by describing a situation that sounds like routing is routing, but the real question is whether the environment is one domain with a shared goal or multiple domains negotiating boundaries. Once you see that boundary, the correct answer becomes a matter of matching the protocol to the problem rather than matching acronyms to popularity. The goal here is to make you comfortable saying, in plain language, what each protocol is trying to accomplish so you can pick the best fit quickly. Before we continue, a quick note. This audio course is a companion to the CloudNetX books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyberauthor.me in the Bare Metal Study Guide series. Open Shortest Path First, commonly shortened to OSPF, is an interior routing protocol designed for routing inside an organization using areas and link costs to compute best paths. Interior means it assumes a shared administrative domain where routers are expected to cooperate, share detailed topology information, and converge quickly when changes occur. Areas are a scaling and containment technique because they allow you to segment the routing domain so that not every change must be processed everywhere with equal detail. Link costs are the metric mechanism representing how expensive a path is, and routers prefer lower total cost paths when choosing where to forward traffic. The practical effect is that OSPF behaves like an optimization engine inside a network. It spreads knowledge of internal reachability and then selects efficient paths based on defined costs. In scenario terms, OSPF fits when you want predictable, consistent routing across many internal segments and when you can standardize configuration across routers. It is a protocol for internal efficiency and fast recovery in environments where you control the rules. Border Gateway Protocol, commonly shortened to BGP, is a policy routing protocol used between networks, where path attributes and administrative intent matter more than simple shortest paths. Between networks means the participating entities are often different organizations or different routing domains, such as an enterprise and an internet service provider, or an on-premises environment and a cloud provider edge. BGP is not primarily about finding the shortest internal path. It is about advertising which prefixes you can reach and choosing among advertised routes based on policy decisions encoded through attributes. Those attributes allow control of preference, path selection, and how routes are propagated, which is essential when networks are peering and when business intent matters. The practical effect is that BGP behaves like a negotiation system. Routers exchange reachability and then decide which routes to prefer based on rules that represent relationships, cost, and risk. In exam scenarios, BGP appears when routing crosses ownership boundaries or when you need explicit control over what is shared and what is preferred. It solves the problem of controlled exchange at the edges, not internal topology optimization.
A simple rule that often matches exam intent is to select Open Shortest Path first for fast convergence inside controlled enterprise environments, because internal networks usually value quick recovery and consistent optimal paths.
Within an enterprise, links fail, maintenance occurs, and users expect internal applications to remain reachable with minimal disruption, which makes convergence time a key requirement. OSPF is designed for that internal dynamic, where routers can rapidly share changes and recompute paths when a link or device fails. Controlled environments also mean you can enforce consistent area design, consistent cost strategy, and consistent neighbor relationships, which helps OSPF behave predictably. In a campus or data center context, OSPF aligns with the desire to maintain stable internal reachability without manual route updates. On the exam, when the scenario emphasizes internal routing across many segments, fast recovery, and a single administrative domain, OSPF is often the best answer. This choice reflects that OSPF is built for intradomain optimization, where shared goals make rapid adaptation valuable. The complementary rule is to select Border Gateway Protocol when exchanging routes with providers or clouds, because those scenarios require controlled advertisement and policy-based preference across boundaries. Providers and clouds are separate routing domains, and the enterprise often needs to decide which internal prefixes to expose, which external prefixes to accept, and how to prefer one connection over another. BGP supports this through attributes and policy control, which allow an organization to influence routing decisions without needing a shared internal topology view. Cloud connectivity often includes multiple attachment points, multiple regions, and hybrid paths, and BGP is frequently used to advertise enterprise networks into the cloud and cloud networks back to the enterprise in a controlled way. This is not simply about using BGP because it is big. It is about using BGP because boundary routing is about relationships and policy, not about internal shortest path. In exam scenarios, when you see language about peering, provider connections, multi-cloud connectivity, or exchanging routes across organizational lines, BGP should rise quickly. The best answer usually reflects that BGP is the standard tool for interdomain reachability exchange and policy control at boundaries. Metric thinking helps you choose correctly when both protocols are presented as options, because Open Shortest Path First prefers the lowest cost, while Border Gateway Protocol prefers policy decisions. In OSPF, cost is an internal measure that can reflect bandwidth, latency preference, or an administratively chosen value, and route selection is generally about minimizing total cost across links. In BGP, attributes and policy determine preference, which might reflect business relationships, desired egress points, traffic engineering goals, or risk considerations. This means you do not choose BGP because you want the shortest path. You choose it because you want to enforce a relationship-driven decision, such as preferring one provider, limiting route acceptance, or controlling which prefixes are advertised. Conversely, you do not choose OSPF when you need to negotiate route exchange with external parties, because OSPF assumes a cooperative internal environment and focuses on internal optimization rather than boundary policy. Exam scenarios often hinge on this difference by describing a need to prefer one link for business reasons, which is a policy signal rather than a cost signal. When you can say, OSPF optimizes, BGP chooses by policy, you can decode many questions quickly. Scaling differences are another major distinction because OSPF uses areas to contain change, while BGP is designed to support broad reach across many networks through controlled advertisements.
OSPF scaling is about limiting how far internal topology changes propagate and how much detail each router must process, which is why area design matters for stability and performance. Areas allow you to keep local churn local, so a failure in one part of the network does not force every router everywhere to process the same update complexity. BGP scaling is about controlling which prefixes are shared and selecting among many possible paths using attributes, which supports large-scale interconnection like the public internet and complex enterprise edge connectivity. In hybrid designs, BGP is often used at the edge to exchange reachability with external domains, while OSPF may still be used internally to move traffic efficiently inside the enterprise. Exam questions sometimes include cues like many sites and segments inside the organization versus multiple providers and peering relationships, which point toward OSPF's internal scaling versus BGP's boundary scaling. Understanding these scaling models helps you avoid mixing roles and creating needless complexity. Consider a scenario comparing a branch network versus a multi-cloud connectivity requirement because it highlights the fundamental problem each protocol is solving. A branch network with stable internal subnets and a need for reliable internal routing is often best served by an interior protocol like OSPF if the organization wants automated internal route management and fast convergence. In that case, the branch participates in the enterprise's intradomain routing plan, and OSPF's area structure can contain changes while providing consistent reachability. A multi-cloud connectivity requirement, on the other hand, is about exchanging routes with external cloud networks, selecting preferred paths, and controlling what is advertised, which aligns naturally with BGP at the boundary. The multi-cloud case often involves multiple peering points and policy decisions about which cloud connection should be primary, which should be backup, and which prefixes should be shared. In exam reasoning, the correct answer is often a hybrid, OSPF inside, BGP at the edge, because each is used where its model matches the problem. The key is not to treat protocol choice as a popularity contest, but as a boundary versus interior fit decision. Security controls matter for both protocols, and neighbor authentication and route filtering reduce risk, because routing is a control plane function that can be attacked or misconfigured. Neighbor authentication helps ensure that only authorized routers participate in routing exchanges, reducing the chance that a rogue device injects misinformation. Route filtering helps ensure that only intended prefixes are accepted and advertised, preventing accidental exposure of internal networks and limiting the impact of a compromised peer. In BGP, filtering is especially important because external peers can advertise large route sets, and accepting too much can create reachability you did not intend or overload routing tables. In OSPF, controlling adjacency formation and area boundaries helps keep internal routing stable and reduces the chance that misconfigured devices disrupt the domain. Exam scenarios that mention partner connectivity, untrusted segments, or unexpected routing changes often expect you to include security controls as part of the protocol decision. The best answer typically implies that routing is not only about reachability, but also about trust boundaries and controlled exchange. A major pitfall is leaking internal routes to external peers because it can cause exposure, security incidents, and unpredictable traffic flows beyond your intended boundary. Route leaks can happen when redistribution or advertisement policies are too permissive, when filters are missing, or when defaults are accepted without review. If internal management networks or sensitive subnets are advertised externally, they may become reachable in ways that violate segmentation and compliance requirements. Even if external reachability is not exploited, the leak can still cause operational issues such as unwanted return traffic paths, unexpected routing load, and confusing troubleshooting due to reachability that should not exist. In exam terms, if the scenario mentions exposing internal networks or unexpected routes seen by a provider, route leakage is the danger the question is pointing toward. The correct response usually includes tightening advertisement policy, filtering, and summarization strategies so only intended prefixes are shared. Recognizing this pitfall helps you choose answers that treat boundary routing as a controlled negotiation rather than as an open broadcast. Another pitfall is poor summarization, increasing tables, and slowing troubleshooting later, because route detail that is unnecessary can become an operational tax. If you advertise too many specific internal prefixes externally, you increase the size of routing tables, increase the load on devices, and make it harder to interpret reachability quickly during incidents. If you fail to summarize internally in a structured way, OSPF domains can accumulate complexity, and changes can propagate more widely than needed, affecting stability and making convergence behavior harder to predict. Poor summarization can also create security policy sprawl because filters and rules must reference many small prefixes rather than meaningful aggregates. In exam scenarios that emphasize growth, operational simplicity, or troubleshooting pain, summarization and route hygiene are often the hidden requirements. The best answers tend to prefer clean aggregation and controlled advertisement rather than maximal detail, as long as it does not create ambiguous routing capture. The goal is clarity at scale, and summarization is one of the main tools that delivers it. A simple memory anchor is that Open Shortest Path First optimizes paths, while Border Gateway Protocol negotiates relationships first because that captures the core intent difference in a single sentence. OSPF assumes a shared domain where routers cooperate to find efficient internal paths and recover quickly from internal failures. BGP assumes boundaries where different domains exchange reachability and choose routes based on policy, preference, and relationship attributes rather than simple cost minimization. This anchor helps in scenario questions where both protocols appear plausible because it forces you to ask whether the problem is internal optimization or external negotiation. It also reminds you that BGP decisions are often intentionally non-optimal in a shortest path sense because policy can override cost for business reasons. When you can recall this anchor quickly, you reduce the chance of choosing the wrong protocol for the wrong layer of the problem. The exam rewards this kind of clean separation because it reflects how real networks are designed. To end with a selection prompt, imagine a requirement set where the organization needs fast failover between two internal links in a data center, strict control of what prefixes are shared with a cloud provider, and a clear preference for one cloud connection unless it fails. The internal fast failover requirement points toward OSPF inside the controlled environment, where link costs and area design can deliver quick convergence and stable internal routing. The prefix sharing requirement points toward BGP at the boundary, where route advertisement and filtering can be applied precisely to expose only intended networks to the cloud. The preference requirement also points toward BGP policy because choosing a preferred external path is a relationship and policy decision rather than a pure internal cost decision. In this scenario, the best answer is not pick one protocol. It is to place each protocol where its model fits the requirement and to secure the neighbor relationships and filters to prevent leaks. This is the kind of multi-constraint reasoning the exam expects because it is how real hybrid architectures are built. When you can justify the choice using the stated constraints, You will consistently pick the best answer rather than the most familiar acronym. In the conclusion of episode 21, titled OSPF versus BGP, which problem each one is solving, the selection rules come down to domain boundaries and intent. Open shortest path first is an interior protocol that uses areas and link costs to optimize paths and converge quickly inside a controlled enterprise environment. Border Gateway Protocol is an interdomain protocol that exchanges routes between networks and selects paths based on policy and attributes, making it the standard choice for provider and cloud connectivity. You remember that OSPF prefers lowest cost, while BGP prefers policy. And you understand that OSPF areas contain change, while BGP supports reach across boundaries through controlled advertisement. You apply security controls like neighbor authentication and route filtering to reduce misinformation and route leaks. And you avoid pitfalls such as leaking internal routes externally and allowing poor summarization to bloat tables and slow troubleshooting. Assign yourself one comparison rehearsal today by taking a single connectivity requirement and stating in one sentence whether it is an intradomain optimization problem or an interdomain policy problem, because that sentence usually reveals whether OSPF or BGP is the right tool for the job. Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.